Tell me what those taste like refrigerated. For those of you listening at home, those were dum-dums that have been refrigerated. All right, we are going to do chapters 13, 14, right? 13, 14, and 15 today. And y'all are on chapter what now? 16. All right, so we're going to be pretty close.
We got our test next week. It's only 11 through 15.
It's only 11 through 15? Yeah. Perfect. And what day is it next week?
Tuesday.
Tuesday.
And then we're doing a review in class tomorrow because we're ahead of schedule.
Good.
So, yeah.
Okay. I will have that hopefully sent out by Saturday, the mock test. I've got a lot going around the rest of this week. But I'll try to have that by Saturday morning, Saturday early afternoon, sent out to y'all for you to do, and then maybe Monday morning we can do a little review going over that, or Tuesday morning, probably Tuesday morning, or Monday morning. Which would y'all think would work best? Probably Monday, just to give y'all a little bit more time to go over it. Cool. So we'll try to do Monday morning. It won't be vodcast or anything. Just kind of show up here an hour before class, and we'll go through some questions y'all have. Does that sound good? Cool. All right, let's get into it. Glycogen metabolism. Glycogen, as we know, is the storage form of glucose. Yes? And it is a polymer of actually D-glucose specifically. It's our most common storage form of a polysaccharide that we have. And it's important that our liver synthesizes most of it, and then our muscle synthesizes the second most of it. Okay? And really, the goal of glycogen is to say, hey, our body needs glucose, so let's store glycogen so that when our body needs it, we can just pull it out of storage and use it, right? So it's in our liver, it's in our muscles. And so when we are fasting or if we're exercising heavily, that's when we're going to break down that glycogen and get that glucose that we've already used up in our blood. The glycogen is highly branched and contains both linear alpha-1,4 linkages as well as the branched alpha-1,6. All right, remember the branched is the alpha-1,6. And this chapter is going to be going over the creation, the synthesis of glycogen, as well as the breakdown of it. So if we are making glycogen, that means we have too much glucose, so we need to store it. And then if we're breaking down glycogen, that means we don't have enough glucose, so we need it. Pretty simple. But those are easy test questions of when would we go through this process. All right. Nice little picture. We have, like we said, liver and muscle. In muscle, the need for ATP triggers the conversion of glucose to glucose 6-phosphate to enter glycolysis. And then in the liver, it's going to be our low blood glucose. So liver is going to determine serum glucose, and our muscle, our ATP needs, our energy needs, like when we're exercising. And so how do we remove glucose from glycogen to use it? Okay. We remove glucose from the non-reducing end of a glycogen chain. So if you go up to the top of the page, you can see the non-reducing end here as opposed to the reducing end. We take it off the non-reducing end. It's just an easy test question. And that continues. We keep taking off glucose until it reaches the 4th unit from the branch point. Okay, and let's see, is there a branch point on here anywhere? Yeah, so here we have a branch point. So here's our alpha-1,4s. Yes, so here's our string of glucose making glycogen. Here we have our alpha-1,6 making the branch, and then more alpha-1,4s going that way. And so we just take these off one by one until we get to this branch point. Okay, something's different. And then we go through a couple other enzymes which are right here. So these are our 3 enzymes. We never get away from them, right? We never get away from enzymes and what they do. It's wonderful. We have three enzymes that are for glycogen breakdown. The first one is glycogen phosphorylase. Second one is glycogen debranching. Third is phosphoglucomutase. Just by looking at glycogen phosphorylase, what do you think it's going to do?
Break down phosphate.
It's going to, there's going to be something with glycogen, and there's going to be something with a phosphate group, right? Just very simply, probably the removal of. Glycogen debranching, what do you think that's going to do? It's going to take the branch off. Really simple. And then phosphoglucomutase, what would you say that's going to do? It's going to turn the phosphate, it's going to take the phosphate from one spot and put it on another, right? So when you're looking at a test question and you're trying to determine what's happening with that enzyme or like what the right enzyme is, it already tells you the answer right there. Cool. First, we have glycogen phosphorylase. So this is going to be our bond cleavage. We're going to take glycogen and we're going to remove one glucose, one phosphate from it. Okay, so we've got our glycogen chain here, either one, and we're going to take off this one unit, and it's going to come off as glucose 1-phosphate. Okay, the coenzyme for that is pyridoxal phosphate. What enzyme? What B enzyme number is that? Or what B vitamin? Sorry, B vitamin, B6, right? Okay. So here's our non-reducing end. We're going to take that off, and we're going to make glucose 1-phosphate, and now here's our new non-reducing end. So all that first one is taking off glucose 1-phosphate. Next, glycogen debranching enzyme is going to debranch it, so it's going to be dealing with the alpha 1,6 linkage that we have. Catalyzes the removal of glucose units one by one from the glycogen 1,4 linkage as glucose 1-phosphate. And then the transferase activity transfers 3 glucose residues from the 1,6 branch point, leaving the 4th glucose bound to the 1,6. So that's what we just did previous to that. Next, the debranching enzyme removes the 4th glucose unit from the branch point as free glucose. So in the first one, we took off glucose 1-phosphate. In this one, it's coming off as free glucose and hydrolyzes the alpha 1,6 linkage. Here we've got it nice color-coded. First step, take off these individual ones as glucose 1-phosphate. Then we get down to our debranching enzyme. And that's going to release these 3 as, it's going to transfer these 3 from this branch chain. It's going to put it on to our main chain, and then it's going to remove that 1,6 linkage, and that's going to go as just regular glucose. And so then now we're left with just alpha 1,4 linkages. And then phosphoglucomutase, what that does is it converts the glucose 1-phosphates into glucose 6-phosphates, which can then just go into glycolysis and be used. Really simple.
What happens with the left blue dots? So like on the second part?
Here?
Yeah.
So this is our glucose 1-phosphate. Those are going to be converted into glucose 6-phosphate by this phosphoglucomutase.
So the whole thing is glucose 1-phosphate?
Those are 10 individual ones.
So that's 10 individual glucose phosphates.
Yes.
All right,
Cool. Do I need to say that one more time from the start? I'll say it one more time from the start. All right. First enzyme is glycogen phosphorylase. Glycogen phosphorylase says, hey, look, we've got glycogen. Let's break it down smaller. So takes each of these off as glucose 1-phosphate until it gets to the 4th from the branch, and then it stops there. Since this is different, now we've got our glycogen debranching enzyme. Debranching is going to take these 3 coming from the alpha 1,6 linkage, put it on our main chain, and elongate it there. And then it's going to take this last alpha 1,6, remove that as free glucose, and then our glycogen phosphorylase is just going to take those off one by one as glucose 1-phosphate. Lastly, phosphoglucomutase is going to come in, glucose 1-phosphate. We can't use that in glycolysis, no. Well, we can use glucose 6-phosphate and convert that to fructose 6-phosphate, and then fructose 1,6-bisphosphate, and then aldolase is going to convert that to dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, right? We're not forgetting that. And there we go. And then G6P can enter glycolysis, produce ATP, and it can also be converted back to glucose in the liver. And the liver is going to send it into our body. The liver is super important if y'all haven't figured it out yet. You'll figure out a lot of lab tests for the liver later in Try 5. Pretty simple. It's just those three. He's just going to ask you on a test, what is the function of this? Or he'll say, this is happening. What's the enzyme? And you'll have to pick out which one. Not too bad. Okay. Phosphoglucomutase uses an intermediate, the glucose 1,6-bisphosphate, but don't really worry too much about that, I would say. Just read that for your own fun and enjoyment. We had a test question on this when we took it here. Let's make it a little bit bigger. All right, so what happens? How does glucose 6-phosphate get into the cell? Okay. So it's produced in the cytosol of our liver cells, and it's transported to other tissues in the blood. What happens is, since that phosphate is on there, it has that extra polarity, so it can't just go through the membrane, right? Because if it was nonpolar, it could go through the membrane. But since it's polar, it gets stuck with the heads, and it gets attracted to those. So we need some kind of transporter here to bring it into the cell. And that first transporter that allows it to get into the cell is T1. Okay, so T1 allows G6P to come into the cell. And now it's actually in the endoplasmic reticulum. I'm sorry. It's in the cytosol, and now it's got to go into the endoplasmic reticulum here. So it's inside of there. And inside of there, we have our glucose 6-phosphatase. Okay, phosphatase is going to take off that phosphate from glucose 6-phosphate, making just regular glucose. And lastly, now that the endoplasmic reticulum, or the ER, has done its job, that glucose now needs to go into the cytosol and then eventually back into the bloodstream. So it's going to go out of glucose transporter T2. So it comes in with T1 as glucose 6-phosphate, and then it's going to leave via T2 as regular glucose. Okay? And lastly, we have our GLUT2 here. Excuse me, that's where cytosolic glucose is transported to the circulation by liver cells, and that's GLUT2. That was our test question, was what allows glucose to go from the cytosol into the bloodstream, and that'd be your GLUT2. So T1 comes in to the endoplasmic reticulum. We have glucose 6-phosphatase. Phosphatase takes off the phosphate group, and then T2 allows the glucose to leave the endoplasmic reticulum, and GLUT2 allows it to go out of the cell and into our bloodstream, thus accomplishing the goal of increasing serum glucose.
What did you say GLUT2 does?
GLUT2 takes it from inside the cell to outside the cell into our bloodstream.
Takes glucose?
Glucose. All right, regulation. Woohoo, more regulation. That's what we want. Allosteric regulation of glycogen phosphorylase. The inhibitors are going to be ATP, glucose 6-phosphate, and glucose. Okay? ATP is pretty much our main inhibitor of most things. And glucose, if we already have glucose, then we don't need to be making glucose, right? It makes a little bit of sense. Same thing with glucose 6-phosphate. Our activator is AMP, right? So if we're thinking of our muscles, right, we're trying to break down glycogen because we've used up all of our glucose through glycolysis, and we need more. So we need more ATP. So that's why AMP is driving this. Covalent modification, this was a test question for us, and there's another one later too. The phosphorylated form of phosphorylase A is active. And then the dephosphorylated form of phosphorylase B is inactive. So phosphorylated is phosphorylase A active. Phosphorylase B is inactive, and it has that phosphate group taken off of it. And we can read about that here a little bit here. So phosphorylase exists in two forms. It's inactive and it's active. Phosphorylation of its serine hydroxyl group, that was, for whatever reason, boards kind of like that. I don't know why, but it's serine, so we know that there's a hydroxyl group on it. Whatever, that's not, y'all can reason through that. Phosphorylation of its serine hydroxyl groups by phosphorylase B kinase activates the enzyme, and is termed phosphorylase A active. Requires pyridoxal phosphate as its coenzyme, and the dephosphorylated form is inactive. It's stimulated, phosphorylase A kinase is stimulated by glucagon and catecholamines. All right, that makes sense. Like glucagon is trying to pump glucose back into our bloodstream because there's not enough. We went over that in chapter 6, so a lot of this is just redundant. We've got it before. But the big thing is he's going to ask which one's active, which one's inactive. Once again, phosphorylation, dephosphorylation. This is just our GPCR from chapter 6, saying that glucagon is a GPCR, whereas insulin was a tyrosine kinase. Right? So we had the whole chapter 5 of GPCR and that whole page that we memorized. And still remember, right? Because we need to know it for the final. Yes? No? Okay. Remember, we had our receptor binds. It binds and it causes that conformational change, causing the alpha subunit to separate from the beta and gamma subunits. And the alpha subunit went. GTP was knocks out GDP, all that good stuff. Yes? If y'all need to, it's like page 50 or something like that. Just look over that real quick. Not that big a video, though, for this test. Or you can just look at it on this page right here. All right, glycogenesis. So here's the other half. Everything before this was glycogen breakdown. Now we're going to make it. All right? Glycogenesis, the creation of. Starts with the conversion of free glucose to glucose 6-phosphate catalyzed by hexokinase or glucokinase. All right, we should recognize those by now. And G6P is converted to G1P by phosphoglucomutase. So if you remember in our glycogen breakdown, we took off individual glucoses as glucose 1-phosphate. So now we have to make glucose 1-phosphate. Okay, and so we got to go kind of the reverse reaction of glucose to glucose 6-phosphate to glucose 1-phosphate. So next, we are going to have 3 more enzymes that we need to remember, right? More enzymes, we love them. And you need to know both sets of these for the test specifically, and know the order, because he's asked the order of them before. UDP glucose, pyrophosphorylase, glycogen synthase, glycogen branching enzyme. Pretty straightforward. So UDP glucose catalyzes the reaction between glucose 1-phosphate and UTP to form UDP glucose and pyrophosphate, whatever. Next step, glucose acts as the glucose unit donor. So it's going to be the same kind of transfer reaction that we saw in, I think, the last chapter when we had the UDP, really long word, right? So it's just kind of like a placeholder. And we're taking off the phosphate group, and we're putting on this UDP onto glucose. And also, the creation of this pyrophosphate bond is just greater energy from when we can break it down and get some exergonic release of energy. So glycogen synthase then catalyzes the transfer of the glucose part of the UDP glucose to a non-reducing end of a branched chain molecule making the alpha-1,4 glycosidic linkage, and thus the glucose chain is elongated by 1. All right. So the taking off of the phosphate and putting onto this UDP just makes it easier to add it onto the glycogen chain. Makes it easier for that alpha-1,4 linkage to be made. Okay, and it's added to the non-reducing end. And then glycogen branching enzyme, as you can imagine, is probably going to deal with something with the creation of an alpha-1,6 linkage, yes. And it's formed by that. And it's also called the amylo alpha-1,4 to 1,6 trans glycosylase, whatever. If you see amylo, remember amylose was just alpha-1,4 linkage, and then amylopectin was alpha-1,6. So if you ever see amylo or amylo, just start thinking alpha-1,6 linkages. Okay. Transfers 6 or 7 residue segments from the end of a 1,4 chain and making a branch chain from them. So as we can see here, it's taking 6 or 7 from here, and it's going to pull them all the way, making the alpha-1,6 branch chain. So knowing the numbers on that is pretty important too. It takes 6 or 7 to make it, and then when we're breaking it down, we break it, and then we stop it at 4, and then the debranching enzyme takes those 3 and moves it down, and then releases the last one as free glucose. It's riveting, I know, but we can power through it. All right, glycogen is important. It's more soluble. The branching makes it easier to store in our body. Increases the number of non-reducing ends, so that means that we can increase the more sites accessible to glucose being put onto it, right? So the more branches that we have, the more places that we can put glucose on. It also increases the number of places that we can take glucose off, so that we can break it down faster, right? So it's like when we're on a field trip in like high school or whatever, and we're on like one of those yellow dog buses, right? And instead of like waiting for everyone to file out the front door, you open the emergency exit in the back, and like people can go in and out both ways. It's the same thing, right? It just makes it faster for things to get in and out. So faster for the breakdown and for the addition to. Yeah. Glycogenin. Dr. Sarkar likes glycogenin. Okay. Glycogen synthase can't initiate a new glycogen chain de novo. He likes that term also, the de novo. Like just by itself or brand new. Can't do it by itself. So it needs a primer. And so what glycogenin is that primer. And it also acts as an enzyme that catalyzes the creation of glycogen. Okay, so it's a preformed, already made alpha-1,4 glucose chain that has at least 8 glucose residues on it. All right, so it's just already there, ready to go, 8 glucoses, and we're going to go from there. So how it works is we make bonds between glucose and UDP glucose with a tyrosine residue of glycogenin. He likes the tyrosine residue also. I'd say this one's a little bit more important than that serine group on the other one. So this tyrosine residue. And the addition of several glucoses up to 8 forms a primer. Okay. So how this looks is we've got our glycogenin, and our UDP glucose is going to be added to our tyrosine residue here, and thus it's been increased by 1, and then we can do that up to at least 8 times. So we start with glycogenin, we add glucoses going this way, and then we can add glucoses this way, and it just branches off, making glycogen. So we can see here the number of non-reducing ends that we can take glucose off of or put glucose onto is just a lot more than if it were just one straight linear line. But glycogenin acts as both a primer and catalyzes the assembly. Need to know that. And it's preformed with at least 8 glucose residues. And then it UDP glucose to the tyrosine residue are the big things for that. Here's where it gets a little bit tricky. So when you're studying, just make sure that you can get these the right way. So glycogen synthase is regulated by covalent modification as well, and the phosphorylated form of it is inactive, whereas the dephosphorylated is active. So it's the opposite of our breakdown of glycogen. So going back, so with our glycogen phosphorylase, phosphorylase B is inactive, phosphorylase A is active, and here glycogen synthase B is inactive, glycogen synthase A is active, but it's dephosphorylated. They're flipped. Okay, so when you're studying, make sure that you can put those the right way, because he asked us for sure, and then everyone was like, "Darn it, those I didn't. I just remembered not enough." So a lot of people got that question wrong. All right, I was reading over this earlier today, trying to prepare for y'all, and my memory just did not come up with a lot, to be honest with you. I don't remember glycogen synthase K3 at all. So either that's because it wasn't on the test and I can't remember it, or I just blanked. So I'm going to let this one be on your own, because I don't think I remember seeing this on the test, and I don't want to just read it to you. Unless y'all want me to read it to you, I can. But what would y'all like? Just keep going? Cool. Hormonal regulation. He likes anything regulation. He loves it, all right? So insulin stimulates glycogen synthesis in liver and muscle. And insulin increases the uptake of glucose by our muscle cells and our fat cells. Right? We've covered this in chapter 6 already. There shouldn't be anything new. Right? If we have too much blood glucose, if we have too much serum glucose, insulin's going to bring it into the cell and store it. Right? So that's going to promote glycogenesis. Okay? Whereas glucagon is going to stimulate glycogen breakdown and gluconeogenesis, right? It's going to say, hey, we don't have enough glucose in our blood. We need it, so let's break down glycogen to put it there. All right, this is all chapter 6 all over again, so it shouldn't be really anything new. So glucagon is going to also block glycolysis, and it's going to save glucose for the brain and other tissues, right? So our brain mostly works on glucose. So what it's going to do is it's going to say, hey, I need to stash this over here so that I can keep thinking and have rational, logical thoughts. In muscle, epinephrine. All right, epinephrine, our fight or flight, and stimulates glycogen breakdown and glycolysis to provide ATP to support our muscle contractions. We have a few glycogen storage diseases that he asked more questions than I wanted to when I took it. And so please be very, very familiar with these when test time comes. All right? You need to know all of them. When we took it, he asked about von Gerk's and Pompei's, and I think one other one. So there were 3 questions when we took it. So von Gerk's disease, or type 1A disease, I think he had it as von Gerk's. And this is for boards too. This was that information. We went over this. We have a defective glucose 6-phosphatase enzyme. All right, what does glucose 6-phosphatase do? It's been a long week, yeah. You're no kidding. Let's go back and look up what glucose 6-phosphatase does. Where are we at? I lost it now. 163.
Hydrolysis
Hydrolysis of
of glucose 6-phosphate.
glucose 6-phosphate. Here we go, glucose 6-phosphatase. All right, so this is the one that's inside that endoplasmic reticulum lumen, right? So our glucose 6-phosphate comes in via T1, and then it leaves as free glucose out of T2. So what happens is if we don't have this glucose 6-phosphatase here, that glucose 6-phosphate comes in and it stays there, all right? So it accumulates. We can't even, that glucose is not going to go out and get into the bloodstream, okay? So what's going to happen is the body's going to say, hey, I need more glucose, and so it's going to keep sending glucose 6-phosphate there. It's going to break down glycogen, send glucose 6-phosphate, but it's never going to get converted into glucose, all right? That glucose 6-phosphate is just going to accumulate and accumulate and accumulate, which is not good. And that is what von Gerk's disease is. So our primary organ affected is our liver, right? That's where a lot of this metabolism is happening. And it's going to enlarge, right? Because we keep sending stuff in there, and it's not going to be converted and taken out. So we're going to have our enlarged liver, and it's defective glucose 6-phosphatase. And it can even lead to kidney failure. All right, so the one he likes, as far as I'm aware, defective glucose 6-phosphatase. We get, it's a glycogen storage disease, and it can lead to an enlarged liver. Okay? Pompei's disease, type 2. I don't think he really emphasized the type 1A or 2. He liked the names. This is a deficiency of lysosomal alpha-1,4, alpha-1,6 glucosidase. This enzyme degrades glycogen mainly in our skeletal muscle, and we see it with muscular dystrophy. We can also see it with cardiac muscle. So Pompei's disease is going to be seen in cardiac muscle and skeletal muscle with muscular dystrophy. Forbes disease or Corey's disease, that's how he'll ask it. He won't ask the limit dextrinosis. This is absence of debranching enzyme, okay? So what does debranching enzyme do? It debranches. Specifically, how does it do it? Yeah, we've taken off all up until the 4, right? Then it takes those 3 from the branch and puts it on the main chain, on the main linear chain, just alpha-1,4. And then it takes that alpha-1,6 linkage and releases it as free glucose, right? Okay? Y'all are as drained as I am. Did y'all have a test today or quiz today or something? What did y'all have today? Cells and tissues?
That's not the reason.
Yeah. Yeah. We had test yesterday, test today, 2 quizzes today, test tomorrow, quiz tomorrow. Yeah. So we're right there with you. But we can do it, all right? Let's just power through it. We'll try to get done a little bit earlier today. All right, so this is absence of debranching enzyme is Forbes or Corey's. So this leads to an accumulation of our branch polysaccharides, right? We can't break it down, so they're going to accumulate. Also going to lead to an enlarged liver, but we can also see it in our skeletal cardiac muscle where we store glycogen at. Okay? So the big difference here is it's the absence of the debranching enzyme, whereas with von Gerk's, it's our absence of glucose 6-phosphatase. Anderson's disease or amylopectinosis. So this is going to be absence of the branching enzyme. Okay? So this is going to cause accumulation of branched polysaccharides. Should it say less? Linear? That makes more sense. I had a question. There we go. Absence of linear polysaccharides because we can't make that branch, right? What's the enzyme that makes the branch? What's the enzyme that makes our branches? The one that makes the branches. branching enzyme, right? Pretty simple. There you go. That was an easy one. It's going to be, and how many does it take from the first branch onto the second branch? 7 or 8. Right? Who said it? That's what I'm talking. That was between the numbers. No, yeah, no hands, right? No hands. All right, so with this one, when we are making branches, 6, was it 6 or 7 or 7 or 8? One of the two. There we go. Transfer 6 or 7 residues, making the branch chain. 6 or 7 residues. So when we're takes off those 3, transfers it. When we're making it, transfers 6 or 7 onto there. Anderson's absence of branching enzyme. In the liver, once again, we'll get enlargement, and we can also get myoglobin in the urine here. So this is, try to pick out what's different between each of them. So this one, we can get myoglobin in the liver. And McArdle's disease is absence of muscle phosphorylase. I think he got off with his indents here. Yeah. So the muscle has high levels of glycogen, and this is when we'll see decreased tolerance to exercise. So McArdle's disease, I think of like a hurdler, is someone who's exercising. And so he's got decreased tolerance to exercise. Mainly skeletal muscle, and you'll see cramps and pains. So like when I try to do hurdles, I fall a lot. I actually tried out for it when I was in 7th grade and did not make it. So bad memories. So that led me to a lot of pain, though it was mostly mental. All right, a little personal story there. All right, some key concepts. So that's pretty much the end of the chapter. Glucose 1-phosphate is the link between the creation of glycogen and the breakdown of it. Okay, so we're going to have to go from glucose to glucose 6-phosphate to glucose 1-phosphate, which can then start making the glycogen chains. And then when we're breaking it down, the first enzyme that we have in the breakdown of glycogen is going to release that glucose 1-phosphate, which can then be converted to glucose 6-phosphate by the phosphoglucomutase. Excess glucose converted to glycogen, mainly in the liver and muscle, when ATP is enough, right? So if we have enough ATP, let's just store it. And if we don't have enough ATP, then it's going to go through glycolysis. Glycogen's degraded to yield glucose. I just said that. And UDP glucose is the glucose unit donor in glycogen biosynthesis. Yeah. Remember, GLUT2 takes it from inside the cell to outside the cell into the bloodstream. All right, T1, glucose 6-phosphate into the endoplasmic reticulum. Glucose 6-phosphatase breaks glucose 6-phosphate into glucose and that phosphate group. All right, go take 10 minutes. Go walk around. Go practice palpating. Do something fun for 10 minutes. Y'all look awful, but still like in a nice way. All right, let's tie it back. Try to get finished here in the next 20 minutes. Y'all can go home, sleep. Y'all have any tests tomorrow? We got 10 pages. That's it. Yeah.
10 pages total or 10 pages in the next chapter?
10 pages total for 2 chapters. Can you believe it? 1, 2, 3, 4, 5, 6, 7, 8, 9. I lied. 11. I'm sorry. It was 11. I'm the worst. All right. If you didn't come get a dum-dum, come get one. Don't be that person. All right. All right. Gluconeogenesis. Yes.
Yeah, good call.
I absolutely can. Is there anything else y'all would like me to go over besides malate aspartate shuttle? While we're thinking about it, or you can just yell at me at the end, or maybe just normal voice me at the end. All right, so gluconeogenesis. We are making glucose from non-glucose sources, all right? So that's either going to be via proteins, amino acids, or that's going to be from fats. All right, this is very, very important. We're going to go through this gluconeogenesis if we need glucose and we've probably already used up our glycogen stores, all right? We got to be able to find new ways to do it, and this is how we are going to do that. A few things here. If we don't have enough glucose, not good, right? We've talked about our brain works pretty much solely on that. So do our red blood cells. Okay, so if our red blood cells aren't working, they're not going to be able to take oxygen to where they need to, yes? And then if our brain is not getting oxygen or if our brain is not getting fuel, that's also very not good. So that can actually lead to coma and that can lead to death, okay? So when we have like diabetics who are hypoglycemic, or we have anybody who is hypoglycemic, like this is very, 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 very bad, okay? So if we have people who do have that tendency to be hypoglycemic, or you have patients that are in the future, just constantly be checking them day to day on like how they're looking, how they're functioning, because this can have huge results if negatively if you have a patient like this and you're not tracking that, and you're adjusting them, and they're not getting better. Like check their diet, you know, like make them do a food journal. Like what are you eating? Are you getting enough sugar to make sure that your body can function? Okay, so like I said, nervous system, red blood cells use glucose, and there's always a certain level of requirement for glucose with all our cells. All right. Test question: glucose is the only fuel that can supply energy in anaerobic conditions. Okay, we already talked about that with glycolysis, right? It can be converted into lactic acid. And it's also a precursor to our milk sugar, or lactose, in women. And gluconeogenesis mechanisms can actually be used to clear products of metabolisms of other tissues from the blood, such as when we're making lactate formed by muscle in our red blood cells. So we can then convert that lactate while we go through glycolysis anaerobically. So we make that lactic acid. All right. Well, we can actually turn that lactic acid back into glucose and kind of make a chain event. So we can use that as a fuel, but it's at a very, very heavy cost when we do that. Glycerol, we can use glycerol and propionate from beta oxidation of odd chain fatty acids, which we will get to later and will be very, very, very exciting. All right, major substrates for gluconeogenesis. This makes a great test question of which of the following isn't, or which of the following is. Okay. Starting off, any of our citric acid cycle intermediates can be a substrate for gluconeogenesis. Okay. So if you ever see citrate, isocitrate, anything like that, absolutely. Pyruvate, right? So we can just, at the end of glycolysis, we can just reverse that, pyruvate, and lactate. So those three, I would say, are the easiest ones to remember. Amino acids, we talked about that a little bit. So we can use amino acids to actually make glucose. We can use glycerol, fats, right? That's where we're going to get it from our fats. The hardest one is this propionate from our beta oxidation of odd chain fatty acids. Converts to succinyl-CoA, which enters the citric acid cycle, and as we know, citric acid cycle intermediates can then be used to be converted into glucose. All right, so propionate, whenever you see that, just think that one sucks. So succinyl-CoA, citric acid cycle intermediate. Okay? Big deal, he asked us a question on this, but this is all just common sense. When are we going to do gluconeogenesis? When are we going to go through this? Right? If we're fasting or we're starving, right? If we don't have that blood glucose or we're not getting it in our diet, we need it. So that's where we'll see that in our fasting or starving conditions. So pretty much anything that is going to have a decrease in insulin or an increase in glucagon, you're thinking gluconeogenesis, right? So you're thinking fasting, low-carb diet, or heavy exercise. Another thing right here is that this process is endergonic, right? Because we are making something. Okay, so we are taking amino acids or propionate or what have you, and we are using energy to turn it into glucose. So this is an endergonic reaction or pathway. Places where this happens, you guessed it, the liver, right? We'll also see our renal cortex and some cells in our small intestine, but those are less important. Synthesis from other precursors, we can see here we have lactate, converts to pyruvate, which can then all be converted back into glucose 6-phosphate, what have you. All right, first thing, we're going to start to the conversion of pyruvate or oxaloacetate when necessary. So anything that can be made into pyruvate or oxaloacetate can be made into glucose or be a precursor for gluconeogenesis. All right, there are two big ones here that we need to know. You need to know what they can be converted into. So alanine can be converted into pyruvate via a transamination reaction. Okay, transamination is what? B vitamin? Pretty sure it's B6. But are we sure it's B6? Sounds right to me. 98%? Okay. All right, so we have alanine is converted into pyruvate, and aspartate is made into oxaloacetate. Okay, so try to sound those out. So alanine, 3 syllables, pyruvate, 3 syllables. Okay, and aspartate rhymes with oxaloacetate. Also, there's another one. Glutamate is to alpha-keta. I think that should be alpha-ketoglutarate. I wrote that a little bit wrong. But that one's really simple because it's got the gluta with the gluta. So that one should be pretty straightforward. Those are boards questions too. They asked you like, what is alanine converted into, and you had to know it was pyruvate. Okay, we'll see this a little bit later on in some other chapters. I think for a test for the final. But for now, alanine, pyruvate, aspartate, oxaloacetate, and glutamate to alpha-ketoglutarate. So conversion of pyruvate or lactate to glucose follows a reverse pathway of glycolysis. Okay, so we were starting at pyruvate, and we're just going to go through glycolysis in reverse. And you guys said there's 3 enzymes that we're going to need to know, all right? Like still a continuing theme. And they're going to skip our highly exergonic reactions that glycolysis typically had, which were hexokinase, PFK1, and pyruvate kinase, right? So those, what we're going to do is we're just going to take glycolysis, and we're going to kind of have these enzymes are going to skip over those highly exergonic enzymes. So all the other ones are the same, right? Because all the other ones are reversible, can go both ways. But these are the ones that we got to jump over. All right, so these 3 are pyruvate. We're jumping over pyruvate kinase, PFK1 hexokinase. And first off, we're going to start with jumping over pyruvate kinase. And this one's going to require 2 enzymes. It's going to require pyruvate carboxylase and phosphoenolpyruvate carboxykinase. And you need to know that order. For this one, you need to know that which one comes first, which one comes second. So it would make sense that the one that has pyruvate is going to come first before the one that has phosphoenolpyruvate, because that's going to be our end product, right? If we're going from pyruvate to phosphoenolpyruvate. That's what we're trying to do. Okay, we're going to jump PFK1 with fructose 1,6 bisphosphatase 1. All right, so we're going from fructose 1,6 bisphosphatase to fructose 6-phosphate. So it makes sense that that's the enzyme that we're going to use. And then lastly, we have hexokinase is going to be jumped by glucose 6-phosphatase. So pretty simple, because we're going from glucose 6-phosphate to glucose. Okay. The phosphatase is taking off that phosphate group. Okay. Pyruvate in the mitochondria. Right. Pyruvate is produced in our cytosol. Yes, it's the end product of glycolysis, and glycolysis takes place in the cytosol. Yes? Yeah? Do we remember that? Yeah. Good. And pyruvate is formed from alanine, right? So alanine to pyruvate within the mitochondria via our transamination reaction. I wrote B5. Now I really got to check if it's B5 or B6. Or was this like board stuff that I'm trying to like mix up with y'all? B6. Sorry. It's been a long day for me too. All right, so our first bypass. Conversion of pyruvate to PEP. It's going to require 2 exergonic reactions. The first one is pyruvate carboxylase. What that's going to do, it's going to phosphorylate pyruvate, and it's going to add a CO2 to it. It's going to carboxylate it into oxaloacetate in the mitochondria. All right, so this is going to happen in the mitochondria. Biotin is the coenzyme for this, right? Biotin is B7, right? All of our carboxylation reactions. And note here we have 1 ATP molecule used for this. Right, so we are using ATP for this. It's converted to oxaloacetate, and oxaloacetate cannot cross the mitochondrial membrane, so it's made into malate, which can cross the membrane, and then once it gets into the cytosol, it's reoxidized back into oxaloacetate. So that makes a great segue for our malate aspartate shuttle system, which let's just take the time to do that right now. Here. So let's start from this side, since we're going in the reverse order. Is that okay? Okay. So we just converted pyruvate into oxaloacetate. All right, we are inside of the mitochondrial membrane, and we want to get outside. Okay. So what we're going to do is oxaloacetate cannot cross this membrane, but it's got a good friend, aspartate, that can. So what it's going to do is it's going to be oxaloacetate. It's going to be converted into aspartate, and glutamate is going to help with that. So glutamate is going to donate its amino group here onto oxaloacetate, making aspartate. Aspartate can then go through this carrier here, and now it's in the cytosol. Okay? And we don't really care about aspartate. We want oxaloacetate, yes? So we're going to take off that amino group and convert it back into oxaloacetate. And what's going to help with that is this alpha-ketoglutarate up here is going to take that amino group off, making glutamate. All right, so boom, done. Oxaloacetate's back over here. Now we can go to our next step. If we were going through the reverse order, and say we wanted this oxaloacetate on the inside here, what we would do is we would convert it into malate via malate dehydrogenase, All right, so we're going to take this NADH. It's going to donate its hydrogen group. So in this instance, we're trying to take the hydrogens from the cytosol into the mitochondria to be able to go through oxidative phosphorylation. Okay, so that NADH is going to donate its hydrogen to oxaloacetate. It's going to make malate. Malate's like, sweet, I can go through here, this awesome slide, right? And now we're on the inside, right? And then malate's like, all right, here's your hydrogen back. Malate dehydrogenase making oxaloacetate.
For the pyruvate carboxylase, it said it was in the mitochondria and it went from like oxaloacetate to malate, but from the mitochondria to the cytosol it changes the state.
Hmm. Honestly, don't know the answer to that question. It would make sense that it could go both ways. I guess depending on the concentration gradient, like which way we need to go. So to me, it makes sense that it could. Does that answer your going over the malate aspartate shuttle system? All right. Okay. All right, so pyruvate carboxylase is going to take pyruvate, it's going to combine it with a bicarb or just a CO2 using ATP, exergonic, using biotin as its coenzyme, making oxaloacetate. Then oxaloacetate is going to go through the malate aspartate shuttle system, going from inside the mitochondria into the cytosol, where it can go through that reverse glycolysis. Then we're going to hit mitochondrial PEP carboxykinase, which is going to decarboxylate that oxaloacetate and make it into phosphoenol pyruvate. All right. Here we are using a GTP molecule to make this reaction happen. Okay, so that's kind of a big deal. It's different than as opposed to just the ATP, and that's going to be used to convert the oxaloacetate into that PEP. That's a good question. Cannot tell you the answer to that question. Did not catch that last try. All right. Yeah, let's just add that to the list. Maybe it's to say that it's coming from the mitochondria. So it's kind of like differentiating where that PEP is coming from, but I have no idea. First comes pyruvate carboxylase. Second comes the PEP one. Now we've got PEP. We can go reverse glycolysis all the way up to what? Fructose 1,6-bisphosphate, right? Cool, so we're there, and the enzyme that we're going to use to jump that is fructose bisphosphatase 1, but you'll probably see that as fructose 1,6-bisphosphate. That one's better. He likes that one a little bit more. So fructose, it was fructose bisphosphatase 1. Yeah. Cool, so that's going to convert the fructose 1,6-bisphosphate into the fructose 6-phosphate. And then we're going to get to glucose 6-phosphate. And in order to jump hexokinase, we're going to use glucose 6-phosphatase. Okay, so the tase is taking off that phosphate group, making just glucose. And we have achieved our goal. Yeah, all right. It's energetically expensive, but it's essential, right? Our brain and our blood need this glucose, right? So we're going to do whatever it takes for that to happen. It doesn't matter the cost, all right? Short-term energy, short-term needs is going to far outweigh the long-term ramifications. Because in theory, the body can get to a point where it's like, hey, like now I can go get some food. Like eventually I will forage and find something to get those carbs in that I need so I don't have to keep doing this. It's expensive, so we are using 4 ATP molecules. We are using 2 GTPs. We're using 2 NADHs. So make sure that you know those numbers, as opposed to glycolysis, typically only requiring just the regular 2 ATP. They are reciprocally regulated in the liver. Right, our principal allosteric regulator of glycolysis was this fructose 2,6-bisphosphate, if we remember that. So this kind of helps make sure that we're not doing both at the same time, right? Because that would be not ideal. We don't want to be going the opposite direction when our brain and our blood need the reverse. So in our well-fed conditions, insulin's high, glucagon is low, brings sugar into the body. So that means we're going to have increased fructose 2,6-bisphosphate, which is going to increase our PFK1 enzyme, which is going to help make pyruvate and go through oxidative phosphorylation, increase glycolysis. Whereas when we're starving or when we're fasting, insulin is low, glucagon is high. It's going to decrease our PFK1 activity because we want to go the opposite way for gluconeogenesis. So glycolysis is decreased in starved or fasting conditions. It seems like I've said the same thing over and over again, and I have, but you'll be surprised when that test question shows up and you're like, got it. Any questions on that chapter? Cool. So really just like 4 enzymes that we need to know. Make sure you know which enzymes they're replacing and what they require. All right, 3 more pages. Ethanol metabolism. All right, alcoholism. We got it. We got here. We should know this chapter by very, very well. No, that's bad, right? That's bad. Alcoholism causes fat accumulation in the liver, produces hyperlipidemia, right? So whenever we see an alcoholic, typically they're a little bit heavier set. So it's going to help increase that that fat creation. Chronic alcoholism can even lead to liver cirrhosis, right? So whenever you see liver cirrhosis, you are automatically thinking alcoholism. That was a test question when we took it. Alcohol has the highest priority of oxidative degradation because it doesn't have a storage form, all right? So that's why our body necessarily freaks out when we drink alcohol, but we can't do anything with it. So our body says, hey, I can't use this as nutrition or fuel or anything. So we need to break this down and get rid of it now. And it can be toxic when accumulated in the body, right? Who here has had a friend who had alcohol poisoning? Right? So we obviously know the effects of how dangerous that can be. Okay? My friend, my roommate in college, he had to have a sternal rub for 5 minutes before he woke up. And he was bruised for 3 months afterwards because he drank 4 Locos all the way down to Corpus Christi, back when they were not regulated. All right? So, yeah. Chronic alcoholism can also lead to a magnesium deficiency due to the low reabsorptive capacity of the kidneys from the renal filtrate. Less important. Ethanol metabolism, mainly in the liver. Boom, right? So it makes sense that if we have cirrhosis somewhere, it's going to be in the liver. This one only has 2 enzymes. It's awesome. The first one is alcohol dehydrogenase and acetaldehyde dehydrogenase. We already know what's going to happen based on these enzyme names, right? We're going to take alcohol, and we're probably going to take off a hydrogen, probably using NAD, making NADH, and the same for acetaldehyde. And boom, that's exactly what happens. Catalyzes the oxidation of ethanol using NAD, making acetaldehyde and NADH. And then our next enzyme is acetaldehyde dehydrogenase. It's going to oxidize acetaldehyde to make acetate using NAD again, making acetate NADH. Okay, so make sure you know that order of you drink the alcohol, so alcohol dehydrogenase, acetaldehyde, and then to acetate. Our NADH-NAD ratio is increased in alcohol consumption. And that is why, because we have made, we have two enzymes that are making that NADH level, okay? So if we are increasing our NADH, we're probably going to be decreasing our citric acid cycle productivity, yes? Because citric acid cycle is going to produce the 3-NADH and the 1-FADH2, yes? So if we don't need, we're not going to be breaking down glucose, we're not going to be breaking down our sugars. So instead of that, we're going to be storing them, right? Because we don't need the energy. We've got the energy intermediates already. So that's why we start seeing weight gain as opposed to any kind of weight loss, is because the things that would normally lead to energy production is now going to be converted into energy storage as fat. So high NADH favors high lactate formation from pyruvate, which can cause lactoacidosis. Diminished pyruvate levels can inhibit gluconeogenesis, right? And in severe cases, liver glycogen can actually be depleted, and that can result in hypoglycemia. And here we have our decreased citric acid cycle intermediates. This MEOS, this showed up on our test. I did not expect it to, but then it waited. Microsomal cytochrome P450 system, or microsomal ethanol oxidizing system. Make sure you know what it stands for. He could easily ask what it stands for. But it pretty much, what it does is it generates acetaldehyde using NADPH, right? What are the things that we're going to associate NADPH with? Just throw out some words at me. Pentose phosphate pathway, perfect. What else? Ribose 5-phosphate, good. Biosynthesis, good. What else? What's another word for PPP? What's another HMP shunt, right? HMP shunt. Good. So, hey-o. We'll try to be really quick and then we'll run out to our cars. Is it raining? No? All right. All right, let's get out of here. So MEOS generates acetaldehyde using NADPH, so biosynthesis, increases in chronic alcoholism, and increases blood levels of acetaldehyde and acetate, because acetaldehyde is going to be converted into acetate with acetaldehyde dehydrogenase. Acetate can be used to make acetyl-CoA. So acetyl-CoA then can be stored as fat, right? Acetyl-CoA is the precursor to all three forms of energy, yes? Or the connector of them. So lipogenesis, it also helps with cholesterol biosynthesis. Toxic effects of it, it's highly, highly, highly reactive. So it can pretty much combine with proteins, nucleic acids, and other molecules, making things that we don't want it to make. And effective ethanol, it interpolates between biological membranes. So I think what it's saying is that it can cross it, or it can become a part of it. So ethanol crosses our blood-brain barrier, right? So that's why we have a lot of, we decrease cognition when we drink too much alcohol, right? It also affects our cerebellum, so that our balance and our walking, our gait is impaired. It increases membrane fluidity. They can alter action potentials, right? So that means our nerves aren't going to work as well, right? So that's why when we're, as chiropractors, if one of our patients comes in and they're drunk or they've been drinking, right, we can actually see decreased results with our adjustments, because they're already affecting the nervous system in a negative way. So when we go in there and try to clear that nervous system, we're not getting the results that we want, right? So if we do see that alcoholic coming in to your practice, really try to help them get the help that they need, so that we can give them the help that they need. affects neurotransmitter release, and cerebral functions are depressed. Big things here, liver cirrhosis is going to be alcoholism. Fatty liver, pretty much the same thing. Can produce coma or death, right? Like we said, like we all had that friend who had alcohol poisoning, and that's deadly. Decreases fatty acid oxidation. So we're not breaking down fatty acids, we're actually making fatty acids. So it's actually increasing our fatty acid production. And then it increases, and that's pretty much what this last one is, leading to fatty liver. Cool. Questions? I didn't beat the rain, I'm sorry. It's coming down. All right, go home, sleep, study for this test, do well, make me proud.